Well, today we are lucky to have Chris Rosen, and he will tell us about a supergravitational perspective on field theory and renormalization group physics. And I remind you that, as usual, the talk will be 30 minutes, and we will have a 10-minute break after 15 minutes. It's a coffee break where you can ask questions, have a small discussion, and also, if you wish, you can go for a coffee. So please, Chris, go ahead.
Great. Thanks much for the introduction, and welcome all to my sparsely decorated living room. It's truly a pleasure to have the opportunity to give one of these short talks. And it's very much going to be aimed at non-experts, but I hope there's going to be a little something for everybody. So indeed, what I plan to talk about is a set of ideas that caught my attention for the last couple of years. And it's all sort of centered around trying to understand quantum field theories at different energy scales. And the way I'd like to do this is by exploiting some techniques, some powerful techniques that come from the study of strings in higher dimensions. So let's see how that all goes. So as physicists, as we try to solve various problems, we're sort of accustomed to learning to squint our eyes a bit and ignore some of the details in order to get at the more broad stroke features that we're after, maybe by making comparisons to other systems we know, or just sort of implementing within our mind's eye this sort of coarse graining. And the Renormalisation Group, as I'm sure you're well aware, is a set of ideas that formalizes this eye squinting. And of course, there's a huge and really beautiful story that accompanies the study of the Renormalisation Group in physics and other physical systems. But the important features that I'd like to take from that, and the ones that you can keep with you for the rest of this talk, are the idea that the Renormalisation Group describes flows in theory space between fixed points, which are theories in which they look the same at all scales. The Renormalisation Group sort of leaves you stuck there if you try to apply it. And deformations away from those fixed points that take you as you traverse from high energies to low energies between one fixed point and another. There are other possibilities. You could flow to gap theories or free theories, but those will be sort of tangential to the main thrust of this talk. And so sort of in a physicist language, these fixed point theories can be described by things like conformal field theories, and their deformations might be couplings to relevant operators like mass terms. And the idea is that as you deform away from the CFT, you run the Renormalisation Group machinery and you flow down towards the IR, you might end up somewhere new and exciting. You might discover a new interacting fixed point theory that you didn't know existed. And the things that I'm primarily interested in are both what sorts of fixed point theories exist within the space of all possible theories. And as I perform this Renormalisation Group trajectory, how do I get to them? How are these fixed point theories related to one another? What happens when I move around in this theory space by performing these deformations? And so a picture that I like to keep in my mind is this loose analogy with this childhood game I used to have. And I'm fully cognizant of the fact that for many of you, this will look unlike any childhood game you had. In fact, there's no place to put batteries. It doesn't plug into the wall. There's no touch screen. But I did a quick Google search to verify that, in fact, you can still purchase these things, probably at like antique shops or something. And it's this so-called Labyrinth Game. And I've tried to illustrate it here with this cartoon. What it is kind of like this box that has on its surface a bunch of holes, maybe some obstacles. And you start off with a marble, and then there's two controls on either side. And the analogy I'd like to develop is thinking of these holes as sort of the location of fixed point theories in the space of all possible theories. And the way that I get between them is by tuning these knobs, which are like couplings to relevant operators. In this case, there's two relevant directions that I can use to set out from this UV fixed point and begin my journey towards the IR. And so the game I have in mind is taking some fixed point theory that I know and love, tweaking the couplings and seeing where I go. So it could end up that I flow to some nearby fixed point. I've sort of discovered that this exists in the space of theories close to my UV. It could also happen that I end up somewhere further, and that in my trajectory, in my path from the UV to the IR, I come very close to that other fixed point, but I don't actually get stuck in it. And this is also interesting because if I study the phenomenological implications of these RG flows, maybe by computing things like spectral functions or studying other observables that catalog the dependence of some physical observable on the length scale at which I've measured it, I may see some imprints of these other fixed points in those observables at intermediate energy scales. So all of these are the sorts of ideas that I'd like to keep in mind and I'd like to explore. Why might you be interested in doing this? Well, I think that there's many ways to answer this question, and perhaps the most poetic or maybe least scientific is that there's just some inherent interest, I think, in understanding what's out there. And this is kind of an exploratory philosophy, just trying to understand what sorts of interacting quantum field theories we can construct and how they're related to one another, what their properties are. But there's another, which is sort of this lower row here, which is that I think it's extremely important to try to quantify and criticize the immense amount of lore that surrounds our intuitions about what the renormalization group is doing as you're flowing from the UV to the IR. And what I have in mind when I write this are the validity of things like A theorems or C theorems. And for those of you that maybe have forgotten what these are sort of notions that when you flow from the UV to the IR, you know you're sort of integrating out degrees of freedom and there should be some loss of the number of degrees of freedom. And these are quantities that are supposed to be cataloging that for you along the flow. And so because you expect to lose degrees of freedom on your way to the IR, these are quantities that should decrease monotonically. And in many cases, under many sets of assumptions, there are proofs that these quantities are in fact renormalization group monotones. And so it's an important program, I think, or at least an important area of research to try to understand what the limitations of these theories are. What happens when I start tweaking a bit the assumptions that went into those proofs? And that will be one of the main sort of thrusts of the research I'm trying to describe. Okay. So how can we go about doing this? Well, there's some ways that you are almost certainly intimately familiar with. For example, when you took your quantum field theory class, you almost certainly computed some diagrams and use those to construct perturbatively beta functions for your favorite QFTs, search for their zeros and identified fixed points in this way. And of course, this is in many cases sufficient and interesting way to get at this problem. But it also has its inherent limitations. For example, you're committed to studying theories with perturbative couplings. And in fact, of more relevance to the situations I'd like to describe today, oftentimes in order to exploit these techniques, you need to assume quite a lot of symmetry in your underlying field theory. For example, at least translational invariance, so that you might do Fourier transformations and work in momentum space. But some of the most interesting deformations away from these fixed point theories might be cases where the perturbations themselves are non-homogeneous in the spatial directions. What I have in mind
should turn off the microphone. Okay, thanks.
Everybody's still alive.
So, sorry, I muted someone who had some problem, so you can go ahead. It's solved now.
It sounds like they had a problem. I hope their name's still on the sidebar. So some of the most, I think, interesting situations maybe would arrive in the context of condensed matter theories, where you have defects that are deforming your fixed point, or a lattice where let's say some mass can take some varying value as you move around in space, or for example, inhomogeneous perturbations in a cosmological setting. And so these are all very interesting ways that you might think to deform a field theory and to understand the physics and the phenomenology of these systems. You need to perhaps find a better method than just perturbation theory. One of those methods might be using lattice techniques by throwing the system on a computer. Again, a very powerful technique that's been exploited with tons of success in many physical instances. but again, has its share of challenges. And the one I'm going to discuss today is to exploit a sort of surprising, perhaps for some people, routine for others by this point, duality that rephrases this problem in field theory into the sort of language of a different physical system that looks extremely different. And that's going to be one of the gravitating theory in higher dimensions.
One question.
Yeah.
What is the advantage of considering inhomogeneous perturbations?
Well, I think the advantage is twofold. The first is that very little is known about such deformations in general, and it provides an extremely powerful sort of prod to get at things, to sort of understand in what sense things like A theorems and C theorems, which often assume translation invariance in their proofs, are robust, also in this context. But also, I think phenomenologically, it's extremely interesting. So for example, lattice systems, as I was saying, or interface CFTs, where you have sort of defects or interfaces between two different theories, all of these sorts of things can be understood in this framework of spatially inhomogeneous deformations.
Okay, thanks.
And I'll sort of, my plan for this talk is basically to show you that indeed, once you allow for spatial variation, these deformations, you can get sort of really interesting variations and on sort of well-known RG flows that you might have been more familiar with, and sort of some surprises along the way.
Okay.
Let's see. My plan was to make it a few more slides before coffee, so let's see if I can very quickly do a lightning round review of how this duality is going to work. So now, of course, it's 20 years past its discovery, and it's the subject of textbooks now and entire semesters of graduate courses, and there's no possible way I'll do it justice in the 3 slides that I've allotted to it. But at least so that everybody's on some common ground, let me just give a very quick motivation to suggest why such a duality might work, and then I'll spend the rest of the time showing why it's a useful thing to explore. So this is a duality that comes from string theory. As I said, it's a theory that has both its namesake strings, but also extended objects, like these brains that I've illustrated in all sorts of primary colors, all sorts of colors in general. And by studying within string theory the dynamics of systems of these strings and brains, well, let's study a very simple system of strings and brains. For example, a stack. We just stack a bunch of brains. They have the strings that connect them, that can end on them. And if one is to study the excitations of this system of strings and brains, one finds that it has the same spectrum, let's say, as that of gauge theory. This is sort of a generic result, and the rank of that gauge group is related to the number of brains that I have in this stack. Those are sort of details, but the important take-home message is that I can describe this stack of strings and brains, it turns out, via the gauge theory that lives on its world volume. So that's one way of understanding this object in string theory. But there's another. If I throw many brains onto this stack, this is an object that carries charge, it has mass, and for a sufficiently large number of brains, it's actually going to bend and warp the space-time that it lives in. And so there's a complementary picture. I can understand this stack of strings and brains also by the sort of fingerprint that it leaves on the space-time that it's embedded in. So sort of the way the excitations and these ripples manifest in the space-time very close to them. Those are the degrees of freedom of a supergravitational theory, generically. Okay, so the idea that I can describe this object in string theory, the stack, the system of strings and brains, either by the gauge theory that lives on its world volume, or by the sort of gravitational background very nearby, gives rise to what's called the gauge gravity duality. And because in the most well-known cases, this gauge theory actually turns out to be a conformal field theory, and the vacuum of that conformal field theory, the imprint that it leaves on the space-time very near the strings and brains, is a very specific space-time with negative constant curvature called anti-de Sitter space, you'll often hear this kind of colloquially referred to as ADS CFT, even in cases that sort of extend beyond these paradigmatic examples. And so one important point I make, two important points I'd like to make before we move on, are that we started off by emphasizing that within the Renormalization Group, there's a privileged role played by the fixed point theories, which are unchallenged under scaling. Those are, so for example, CFTs could provide examples of those fixed point theories. And now I'm telling you that a CFT secretly also has a description in terms of a gravitational background known as anti-de Sitter space. So one important feature, perhaps the defining feature of any duality worth its salt, is that it comes hand in hand with a dictionary that allows you to translate quantities on one side of the duality into those on the other. And so, for example, if you open up, to page 7,342 of this dictionary, you'll find that bulk modes, operators such as a gravitational scalar field that lives in this gravitational bulk, is dual or encodes in some way the physics of a scalar operator in the gauge theory. The graviton mode encodes that of the stress tensor. And so, this is pages and pages of very carefully and by this point extremely well checked dictionary entries that provide for you an explicit mapping between degrees of freedom on either sides of the duality. So the fact that it exists is a very powerful bit of information that will help us to unravel the physics of these RG flows. So it's now 16 minutes since I've started, and I think that it's an excellent time to stop and do our little coffee jaunt. And then in the remaining 15, we'll go to the details.
Yeah, so we stop for 10 minutes. Is there any question? Comments?
Did you draw the pictures by hand yourself?
I did.
Mm-hmm.
I've had a lot of free time these last
Okay, so let me make one comment, Chris. So, okay, my very rudimentary understanding of what you're talking about, basically, from what I hear, this kind of duality has only been shown in a case where you have, this space, gravity in this space that is anti-de Sitter, so with a cosmological constant that's negative, basically, and I think in 5 dimensions. So, where are we in terms of, how relevant is that for our universe?
That's a good question. So the original example is indeed the one that you sort of relayed. It was between anti-de Sitter space in 5 dimensions and n equals 4 super Yang nulls in 4. But in the 20 years since, there's been a whole universe of new examples, theories in different dimensions, and the maps between them made incredibly precise and checked using extremely sort of high precision techniques, both in the field theory side and in the gravitational side. It's a little bit different than the question you're asking, which is more like, can we use this to describe the world that we live in? And the perspective that I'm going to take here is that I'm not trying to find a dual for the standard model. I don't even know if that exists. It may not, and if it does, it's extremely complicated. However, within our everyday existence, there exist things like high temperature superconductors and the quark gluon plasma, which is produced at RIC, and a ton of systems whose broad stroke features may be able to be sort of understood in a universal sense by studying the strongly coupled field theories that we can get our hands on via this duality. So I'm not trying to make sort of a precision phenomenological match to the universe that we live in, but rather to understand systems that we study using gauge gravity duality.
Maybe can I add a comment to that?
Yeah, of course.
So even though Chris is going to look at the case in which the field theory living at the boundary is in flat space, you can also replace that flat space by an FRW universe, for example. And then you can use this duality to understand the dynamics of strongly coupled matter in a cosmological setup.
Okay.
Like some people are trying to do.
So I thought that the idea is with this duality is that then you can map all the things in a universe with gravity to another space with one less dimension, one less spatial dimension, where there is no gravity. You just have strongly coupled quantum fields. So then gravity would be an illusion, right? If you think that we live in this boundary and there's no gravity there.
That's not precise. I think the statement is that on the side of the duality where the field theory lives, there is no dynamical gravity. But you're free to prescribe that your field theory lives on any predetermined metric, and that can be an FRW universe.
Okay, so this would be also a gravity that is present in this boundary, but yes, it is fixed somehow, so there is no time essentially there.
Yeah, it's a background for the
metric. It's a background, okay.
In principle, it's just a background that you are free to specify, and then the duality will tell you what the matter does in that background.
Okay. But it's not like general relativity, because in general relativity, the curvature of space-time always responds to the mass energy.
Yes, I'm trying to get to that. So this is the conventional formulation of the duality, but some people, including myself, believe it's possible to actually generalize it so that at the boundary, this metric that you're prescribing is not something fixed that you prescribe once and for all at the beginning and then you look at the behavior of matter, but actually something that you prescribe to in a way that it obeys Einstein's equations, okay, reacting to what the matter is doing. So this would be a setup in which the matter is strongly coupled and fully quantum mechanical, and it's described by the 5-dimensional anti-de Sitter side, and the metric that is coupling to this matter is classical or semi-classical, but it evolves reacting to the matter according to Einstein's equations at the boundary. This might be possible.
Mm-hmm. Okay, thanks. Maybe there are other questions.
But I think, I mean, if I may add also to this that he was saying, I mean, David was talking mostly about something that would be an application of ADS-CFT. Not, I don't think it would be the use of ADS-CFT as a fundamental theory of fundamental quantum theory of gravity.
I agree.
It's how it can be used for applications, I think.
I agree.
Well, another application in the spirit of cosmology, no? For example, we don't understand presently Big Bang singularities, how to treat that quantum mechanically, no? Because we don't have a theory of quantum gravity. And through ADS-CFT, maybe you could understand that just by studying field theory without gravity. In principle, it provides the tools to investigate that. No, still a difficult problem, but it's another possible application. Well, if there are no more questions, maybe we can continue.
Okay.
Yeah.
Great. All right, so let me go quickly here. So indeed, over the coffee break, one important point that was mentioned is that the duality is holographic in the sense that it includes, in the gravitational side, the dimensions that are shared with the world volume theory of the branes, but there are also directions that are orthogonal to those branes, and one of them plays a privileged role, and I'll sometimes call that the radial direction. So particular direction orthogonal to the stack of branes. And via the dictionary, of the gauge gravity duality, that radial direction encodes in a way that can be made precise the energy scale of the gauge theory. And this really reveals its power in understanding renormalization group physics on the gravitational side, because you've encoded those energetics into a sort of physical space-like direction in the higher dimensional bulk theory. And so the way that an RG flow looks in this gravitational, on the gravitational side of the duality, is I look in my dictionary, I understand that the coupling to some relevant operator is tunable by changing the boundary conditions of my bulk fields. And so I go to that fixed point theory, the asymptotically ADS region of my spacetime, and I provide the boundary data that corresponds to the deformation that I'd like to apply. And then I just sort of integrate in, solving the Einstein's equations. And I integrate from the UV down to the IR. And by the time I've finished, I have in my hands really a sort of picture of that RG flow geometrized. So it's that RG flow in the gauge theory encapsulated by a bulk geometry, a solution to the bulk equations of motion. And so in the remaining slides, what I'd like to do is just show the result of the hard work that goes into solving those bulk equations of motion, and look at some novel RG flows that we're able to extract once we've accomplished that task. And so again, this will include very little details. I just want to give a flavor of what exists and talk about the sort of phenomenology as it arrives. So one interesting example is you can take your CFT and you can deform it by giving an inhomogeneous mass, so sort of a mass that varies sinusoidally for some, say, scalar or fermionic bilinears in your gauge theory. All this can be made extremely precise. It depends on the details of the theory that you're looking at, but we've done it in various dimensions and for various theories, and this is sort of a sort of generic flow that you can often find. So you take your mass, you let it vary sinusoidally, and what can happen under favorable conditions, I've sort of illustrated in this right plot. You start at the fixed point, you deform away from it, and as you travel down to lower and lower energies, you in fact find that you come back and end at the exact same fixed point theory. And this is extremely surprising for many people, because there's in fact results and proofs that tell you that as long as your couplings are, as long as you're studying deformations of a unitary quantum field theory, such a thing should never happen. But again, all of these results are hinge on the fact that the deformation itself has preserved the Poincare invariance. And so once you give that up, much less is known. And this turns out to be most a generic flow that can happen in many cases. And there are other surprises. For example, as you turn up the strength of that deformation, measured in units of the wave vector that I called K here, you can explore more and more of the nearby theory space. And in fact, you can sort of start to sense the location, the presence of nearby fixed points. And those appear as sort of intermediate scaling regimes that you can identify when you look at the bulk solution. So the fact that these are called, that these start and end in the same place, led us to call them boomerang RG flows. And we have explicit examples.
Chris, concretely here you are taking ADS4 with some dilaton field also?
Yeah, so, well, as a concrete example, you can do this in the ABGM theory. And so this has a bulk ADS4 solution. And what you do in that case is you can actually even construct these, you can even construct supersymmetric examples of these. And what typically happens in that case is that you turn on a mass for a particular scalar bilinear, and then a corresponding mass for a fermionic bilinear that looks like the gradient of that of the scalar term. And so, sorry, it's the other way around. You turn on the mass of the fermion, and the scalar mass goes like the gradient of the fermion mass. And so, indeed, using the dictionary, because we understand ABGM theory so well, you can identify exactly which operators are driving this deformation, exactly what's happening. But similar things happen also in n=4 and in other theories as well.
See, but these fixed points z=1, z=5 are other ADS4 solutions with some other.
Good. Yeah, these are details that I wasn't going to get into, but I'm happy to talk about it. So indeed, those other fixed points that you can find, one of them that could happen is, let's say that I took the exact same operators, but instead of making the deformation inhomogeneous, I just turned on a homogeneous deformation. Same deformation, but it's not spatially varying. It could happen in that case that I flow to another fixed point. If that's true, then once I turn on a spatial variation, I can no longer flow to that fixed point, but I can sort of come asymptotically close to it in the limit where the strength of the deformation that I've called gamma here, for example, is much larger than k. It's kind of the k goes to 0 limit while keeping the deformation large. So that can also happen. The z equals 5/2 is just an example of what you might call a hyperscaling violating fixed point. It's another fixed point that you might identify, and your observables that you compute will have a scaling that sort of receives the imprint of that nearby fixed point. So this is just a particular example of which there are many, but this sort of thing can happen as generic.
Okay, thanks.
Good. Another interesting class of deformations are the so-called Janus deformations. So these are, so you construct these by taking your CFT, and on half space, you give the Yang-Mills cup one value, and then on the other half, some other value, and you can interpolate smoothly between them. You can make it an abrupt cutoff. You sort of have this interface CFT, and these are also simple to construct in ADS CFT, in gauge gravity duality. So once you have the bulk of these, you can construct variation, or you can construct versions of these that preserve supersymmetry, that preserve conformal invariance in the directions orthogonal to the interface. And this is extremely interesting because these have been studied both in field theory, but very little is known about the details of what's happening on the interface or the phenomenology of these things at different energy scales. And once you have the bulk solution, it becomes possible to probe all of this in extreme detail. A sort of related example, and one of our most recent interests are so-called RG interfaces. So in order to construct an RG interface, you can take your CFT in the UV, and then you just imagine.
Can I ask you one thing about these Janus solutions?
Yeah, of course.
So at the interface, there are no localized degrees of freedom, if I understand that well, right? It's not like a defect CFT.
Yeah, generically there's not, but there are sort of, so Janus as an umbrella includes many examples of which what's happening at the interface is much less understood than in the sort of canonical example where it's truly an interface and not a defect. There's no degree. So in the canonical example, there's no degrees of freedom present on the interface itself. But I've called Janus basically any interface such that the left and right hand CFTs are the same up to the values of the couplings that are in them, to distinguish it from the RG interface that I'll discuss on the next slide. And in the more generic examples, it's an open question what's happening exactly on the interface itself. So a more generic Janus deformation might not include only varying the Yang-Mills coupling, but also varying values for masses of scalar operators, let's say on either side as well.
And you're saying that in some cases it could be that you have a defect CFT instead of an interface CFT?
As defined by degrees of freedom on the interface itself.
Yeah. Okay.
Yeah, it's something that we're trying to understand now by trying to understand what's happening with so-called defect entropy and things like this, which indeed you should be able to measure via holography. Okay. So the holographic solution, the gravitational solution, tells you that there's something interesting that's happening at the defect itself, because it's kind of a weird singular part of the geometry. In fact, the geometry itself is completely irregular, but when you try to understand it holographically, you need to understand it as in a sort of Tuckerman-Graham sense, as you unravel these the most sort of natural set of coordinates, and sort of understanding exactly how to patch them together at the interface is a bit tricky, and that's crucial to understanding exactly what's going on at the interface, which is why it's hard for me to answer the question in more detail.
Okay, thank you.
Yeah, so then there are these closely related RG interface solutions, which are sort of hot off the press, in which you take your CFT and you turn on a deformation in only a very small localized region. And what happens then, or what can happen, is that as you flow to the IR, you end up with an interface solution between two distinct conformal field theories. And so that again has the same issues that were just raised on the previous slide. I'd like to understand what's going on at the interface itself and what the sort of phenomenology is between these, between this juncture. And the way that you can do that is again to use the holographic toolkit. So I'll go very quickly through these next slides so that I have some chance of finishing. But the idea is that we go through all this hard work, exploiting the duality, solving the bulk equations of motion, and the output of that program is this set of geometries, which are sort of like the samples that we've collected. And the next step in the program is to collect data from those samples to understand what's going on in the dual gauge theory. And one thing you might think to compute are things like spectral functions or other linear response observables, Green's functions, two-point functions, things like this. And in the gravitational side, it's very simple to do so. You're just studying linear response. So you let your bulk solution, you perturb it and study the linearized fluctuations around that background. And so this is the closest thing I'm going to show to a real formula or data. And the axes themselves, the colors, nothing really matters, except I want to impress upon you the fact that by using this duality, we can make gauge theory plots that detail gauge theory observables and their behavior as we change the energy scale. So what I've plotted here is a spectral function for a particular operator. This turns out to be an operator in ABJM theory as a function of energy along the horizontal axis. And this is a plot of the spectral function for the boomerang RG flow. So what you can see is that at low and high energies, these curves have the same slope. That's indicative of the fact that they're probing the same fixed point. But as the strength of the deformation grows from the top curve to the bottom, you see the emergence of this new intermediate energy scaling regime, which is showing you that there exists a nearby fixed point as well, and sort of leaving its mark in the observables. And so this is sort of the manifestation of all those ideas that I was trying to introduce. You can also compute things like entanglement entropy, and holography again gives you a sort of well-worn toolkit for doing so. In this case, you're studying minimal surfaces. And the reason this is interesting from a renormalization group perspective is because there exists the idea that by studying the dependence of that entanglement entropy on, say, the strip length between the regions that are entangled, you can construct what's called an entropic C function. And it's been proposed that this entropic C function should behave like the more familiar A and C functions in the sense that as you go from the UV to the IR, it should monotonically decrease. But it's very simple to evaluate this in, say, again, the RG boomerang flow, which is a plot that I've provided here. And you can see right away that it's not monotonic. And the reason that it is able to evade these claims is, again, the fact that you've explicitly broken Poincare invariance. Okay, and I'll skip quickly through these last guys because they're more to impress you with the sort of regime of possibilities that holography provides, other than to say anything very specific. But you can also heat up these RG flows and study the temperature dependence in any of them by adding a black hole. And in this case, nearby fixed points typically leave their mark on thermodynamic scaling relations. And you can use those sorts of observations to try to construct or to try to find within your bulk theory examples of interesting phase diagrams that look like systems that you might be interested in, either in the laboratory or beyond. And so this brings us indeed to the close of what I'd like to share. The big idea being that understanding the behavior of field theories, different energy scales, is an extremely interesting program, and that we can get a really good hold on that, and we can extend and progress this program forwards by using the surprising duality that comes from string theory, which has opened new directions and indeed new questions. I think personally the most pressing of which, and the one that I've been devoting most of my time to, is to understanding how we should extend things like A theorems and C theorems to the case where we've lost Poincare invariance because we've studied inhomogeneous perturbations. And I think trying to understand in what sense the degrees of freedom are decreasing in these sorts of flows as well, and what's keeping track of those degrees of freedom will be an extremely important result that will have implications for many aspects of physics. So that's what I'd like to tell you. Thank you.
Thank you. Questions? Well, I have one. Presently, there is no counterpart of the C theorem for in the case where you don't have a Poincare invariance.
No, and I think until recently, it was sort of an out of sight, out of mind thing. I mean, there was no good reason to believe that things like A's, like anomaly coefficients, A theorems and C theorems wouldn't hold also in those cases, even though nobody really studied it in much detail. But you know, there exist these entropic, there's these entropic A functions and C functions, which many people expected could work in those situations, but we have counterexamples, such as the boomerang flows in which they don't, and also people have found in more mundane theories examples in which they're violated as well in systems that don't preserve Poincare invariance. So there's currently no good candidate in this case.
I see. Thanks. More questions? Well, I have another one. You showed a phase diagram which is very reminiscent, of course, of the QCD phase diagram. In which context you plot this?
Yeah, well, it was meant to evoke your favorite system, I guess. So indeed, people have used holography to try to mimic the QCD phase diagram. And that's something that's been done with various degrees of success, and people continue to study those sorts of things. Also, the phase diagram of strange metals and things like this. And all of these have sort of very broad stroke holographic counterparts.
No, I know, but my question is if this is a cartoon of some calculation or...
This is indeed a cartoon of some calculation. In this case, it was more evocative of a sort of strange metal where you have a quantum critical point at 0 temperature, which you can arrive at. So this horizontal axis is the strength of some coupling, which is sort of like detuning away from criticality by turning on some defect or some by the introduction of spatial inhomogeneity. And so what you found in this case was a first order line of phase transitions, and above that you had a region of sort of CFT2 scaling, CFT1 plus 1 scaling, which is sort of reminiscent of what people call the semi-local quantum liquid that is thought to exist in these strange metals. But these are things that you can kind of engineer almost at a phenomenological level by tweaking your bulk Lagrange, and it's much harder to find them in honest to goodness top-down settings where things are much more tightly constrained.
Okay, thank you. More questions? Well, if not, we thank Chris Rosen again for this very nice introduction and talk to this very interesting topic. And thank you all for participating.
Okay. Yeah, thanks guys for coming.
Thank you very much.
Thank you.